so it's physically located on the same site as the X3 Exadata. And the scripts which were running by JMeter were using CX Oracle Python module to connect to the database. So this is what we observed from the database. And these are the results. That results for whole of the tests, so from the beginning till the end. On the X3 side, it took 35 seconds. And whenever they were running the same test on Exadata CC, it took 160 seconds, so longer. And that was the problem. And this is the results. This is the result from the X3 side, from the JMeter, because this is what people who made the test showed to us. So look, guys, this is what we see. This is how results looks. And this is X3. So the basic and the most important task, let's say, the procedure, the main, the most important task from it, which is some kind of actions, took from on X3 database like 10 seconds. And the other another important piece of the test was user logons, those 50 parallel sessions. And on X3, it was done in almost 2 seconds. But when we look at the same test and results on the CC side, we can see that these tasks, those pieces, took longer. On Exadata CC, the first task took like from 35 to 70 seconds. And logons, just basically logging into the Exadata CC, took like 15 seconds. So it's about 7.5 times longer on Exadata CC. And that was the first, let's say, message which we received, that there is something wrong. So basically, the first thing which we did, so we looked inside the active session history, and we started to examine the situation from that perspective, to correlate the tests and the timeline of the test with the events on the database. And basically, what you can see on that slide is the results on the JMeter from the CC side, and on the bottom of the slide, you can see the active session history from Performance Hub from the database. And basically, they are correlated in the time manner. So basically, they fit each other. So you can see here that. Can I ask you people to mute the microphones, because someone is interrupting? Okay, thank you very much. So basically, what we can see here, that the first thing is user logons. So user logons from the database perspective are connected with row log contention, and this is important information. This is the first thing which we will examine. But another important information which we can see here is that during the yellow, let's say, task, the database activity was almost none. So from the database perspective, the activity and the longer response on the JMeter side, which was observed, is not correlated with the DB time, with the activity. There was non-activity, and the performance was poor. So this is something which we wanted to face with, that someone is telling that the performance is poor, but okay, when you look on the database, it's not so simple to recognize that, let's say. So then we started to dig into particular SQL statements which were used during the tests. And there are three most important, let's say, SQL IDs which we were focusing here on. And as you can see, the first one is the most active one, let's say. And we started to compare the time per execution, database time per execution per SQL ID on Exadata X3 and Exadata Cloud Customer. So from that perspective, what we have learned is that for the most important, let's say, SQL ID for the activity, database time per execution on Exadata X3 was longer. That we have like 900 milliseconds on X3, more than 900, and we have 700 of milliseconds on CC side. So for that particular SQL ID, DB time per execution is lower on Exadata Cloud Customer. So it does not correlate with the information that database is slower. It's not slower. It's on that perspective, you can see that for that particular SQL, it is even faster. For the another SQL statement, that was another kind of select which was used during the test. What we can see here, database time per execution, 615 milliseconds, and on Exadata CC, 471 milliseconds. So another case when another important SQL is shorter on, let's say, database time is shorter on CC side. So the same information we cannot see for that particular SQL that database is slower and there is problem on the database. Okay, let's jump into the third SQL, which is here very important, and this one is connected with user logons. And this is the one SQL which was connected with this row log contention. And in that particular case, indeed, database time per execution was much faster on X3 than on CC, mostly because it's correlated with the row log contention. So when we looked into the AWR reports, also here you can see from the elapsed time global statistics that those, when you compare X3 and CC with those particular SQL statements, SQL IDs, you can see that total elapsed time is longer per SQL ID per on Exadata X3, despite one case when we are talking about this user logons, which is connected with update. The same here, when we look at the database time in the AWR report, we can see here that it's a little bit longer. The overall report shows that DB time for X3 is longer than bigger than on CC. So and one more thing, wait events for both Exadatas. As you can see, DB CPU is a little bit lower on CC, and the one of the most the most important wait event here, which you can see on the top timeout foreground events, it's NQE takes row log contention on CC side, which is connected with user logons. And the space, you can obviously see that here on the screen. So conclusions, user logons is 7.5 times longer, and they take longer on CC side. That was something strange, because basically, as you could see, it was connected with more time spent on row log contention on CC side and then on X3 side. It is not the case then that the logons on X3 side were not connected with row logs. There were also a lot of row log contention on X3 side, but they were not so big as on CC. So they were 7.5 times. It transformed on 7.5 times longer logons on CC side. Specific execution of SQL IDs and particular SQL ID takes the same time when compared to the X3. Beside, of course, the SQL, this SQL statement, which is connected with user logon, which is connected with that particular update statement, which suffers from when query takes role of contention. When you look on AWR reports, you can see that overall role of contention on CC side is about 24 seconds of overall DB time. So when you look on the 160 seconds, which is the result for the JMeter tests, and you will subtract from it the role of contention, it will not explain the differences because it's still big on the test duration when you use it on X3 side. Because the differences in SQL statement execution on both exadatas are quite the same, where there is no big differences in SQL executions. Those differences do not explain these longer results of JMeter tests when you look at on the results on that level, of JMeter. So the conclusion is that the reason for the differences should be searched outside the database, because inside the database you cannot see the time which makes the difference. And basically this is the intro. Kamil, now is the case of the role of contention. If you could explain that.
I'm unmuting myself.
Yeah.
Okay. Okay. So if you see that TX role of contention, what do you say? Not my problem as a DBA, right? Go drink yourself, because NQTX role of contention is well, usually not a DBA case, not something that you can tune, except of course a few cases like lacking of foreign keys and so on. But usually TX role of contention is not a DBA problem. So let's look closer. I will share my desktop, and here it is. Okay, cool. This is my desktop. So let's look closer on what has happened, what a bit Radek already told you. If we look from top down, we will see that SQL elapsed time here for X3 for all database is a bit shorter even than on X7. So SQL execution elapsed time is a bit better on X7. And you will see that the only thing that actually differs is NQTX role of contention. This is our wait event that we were talking about, which took on average 38 milliseconds on X3 and on average 92 milliseconds on X7. So that's 3 times longer. Okay, so in order to actually understand everything, as usual, we have to go first bottom up to be able to diagnose everything later on up to bottom. So first of all, let's answer ourselves one question. What actually a TX roll contention is, and how exactly locks are working are implemented inside Oracle database. I'm sure a lot of you already know exactly how it is done, but for those of you who are wondering, let's just say that we will use a very simple Express Edition database because we can, and Express Edition 18C is really cool. It has almost all enterprise features. Okay. Awesome. Keep going, keep going, keep going, keep going, keep going. Okay, so I made this virtual machine much slower on purpose to simulate some things. Okay. Using memory target, no, okay, cool. We will use one of the PDBs. Cool. Awesome. So our table is in file 22, which resides in this table, this data file. In order to show you what lock actually is, how it is implemented on the low level, and how Oracle is keeping tracks of the locks, you should know that, well, I will use Rico2 tool, which is a copy of BBED, and it maps BBED functionality in, well, very wide scope. But since this tool lets you to access the data files directly and omitting all the security from the database perspective, you should always remember that on production environment, this software should be considered as malware. Okay, because Well, it is a bit like malware, but I love it. So let's check data object ID for our employees table to show you what's going on. Okay. I will go to block 131. Let's see what do we have in here. We have 98 rows in the database block. And I will modify one of those rows. So from this session, I'm going to do update employees, set salary equals salary, where employee ID equals 100. Okay, so I modified exactly one row. This modification has started a transaction which has its own ID. This ID consists of three parts. If you check the $V transaction, you will see each part of this ID. So you will see undo segment number, click slot, and sequence number. And if you look at it, those numbers are encoded in hexadecimal in here. So we have 8 as a byte, 1 as 2 bytes, and I think 4 bytes for 2830. When we checkpoint and force Oracle to go with the database block to the disk, we will see that something similar in a structure called KTBBH. In this structure, we will be able to see not only data object ID of our object, but also something called ITL lists. This is interesting transaction lists, which consists of two structures. One is undo segment number, and the other is undo block address. Sorry, one is seed ID, of course, and other is undo block address. Those two structures are in structure list called transaction block interesting transaction list. So if we look closely, we will see that our seed is in here. I hope you can see it. So we have 2 bytes for our undo segment number, 1 byte for a slot, not a slot, a slot. No, sorry, 2 bytes for a slot and 4 bytes for sequence number. And this is the exact number the exact ID of our transaction. Our XID is encoded in here. So what does it mean? Well, it means that all the transaction numbers are actually being held in a database block header. So in here I have 1, 2, 3 interesting transaction lists. You might think that this means that I can have only, for example, 3 transactions modifying this block, but this is not true. If I start different sessions and different transactions, okay. So if I start different sessions and different transactions, I can fill up all other interesting transaction lists. But if I start another transaction, so 4th transaction, this structure KTBBH will grow, and another 24-byte structure will be added. If we hit the limit of the block size, actually, the limit of the free space, Oracle won't be able to allocate more transactions in the database block. And then you might see a rarely seen wait event, which is NQITL wait. So one of the transactions would have to commit to make interesting transaction list free. Okay, so makes not much sense yet, because you might say that, well, okay, Kamil, but locks in Oracle are not being held at the block level, but on the row level, right? And well, of course, you are correct. In the block, you only have a list of transactions that modify rows in that block. So where is a pointer to the row? Of course, not in here. The pointer is directly in our row. So if we find which, okay, so I updated a row with employee ID equals 100, and the structure of employees tells me that employee ID is the first column, so column 0. If I look for column 0 that has value type number 100, I will find the first row in the first slot. And this is my number, character. So 1, 2, 3, 4 time something like this. Yeah. Okay. So this is my row, right? So this is my row at the block level. And in here, actually, I have a pointer that says which transaction is holding a lock on my block. So the row is constructed like this. At the beginning, you have a row flag. A row flag that says, well, this is a row, and this row is present, is not deleted, and the whole row is in this block. And 2C means exactly this. This flag means that the whole row is inside a block, it's not deleted, it's not fragmented, and so on. And after the first flag, we have a lock byte, and this is our byte. This is a byte that we are interested in. In our case, a log byte says go to the second interesting transaction list in the queue. Sorry. Okay. So this is my first one. This is not it. And this is the second one. And this is it. So this log byte in here points to the interesting transaction list inside a database block header, which holds ID of the transaction that holds my my row, that holds a lock. And since this transaction is active and we know that it is this registered transaction, no other transaction is allowed to modify this this data in the block. No other transaction is allowed to go to this log byte and change it or change the interesting transaction list, the interesting transaction list structure. So when another session is trying to do that, for example, from Python, there's a reason why I'm doing it from Python, don't worry. Ah, shit, I need permissions. Sorry, and sorry for that. Okay, I will use Python later on. For now, I will just use remote SQL plus or no, SSH to be quicker. So what happens now in this session is that a session locates this row in here in the database block. Then it goes to the lock byte. It checks interesting transaction list structure, and it checks if the transaction is actually running. This is a simplification of what actually is going on. Quite big simplification because there's much more going on, of course. But more or less, that's what's happening. And since there is a running transaction, this session is going to wait for someone is chatting. Someone asked something. Yeah, true, Pete. So this is a simplification on how Oracle manages the queues. Okay, how Oracle manages row locks, not the queues, but the row locks. So of course, when I commit from this session, let's see what is going to happen on the disk level. our lock changed from 2 to 3. That's pretty well obvious, since another transaction just allocated another slot, in interesting transaction list, this slot, and now another transaction is being active. And we have a match, right? So right now, this one is holding a lock, and so on and so on and so on. So each and every session that needs to get a lock will have to go through the process, go to the log byte and go to the transaction list in order to do the job. Now, why? So why there's a problem? Because the same mechanism was on Exadata X3, the same mechanism is on Exadata Clouded Customer, the same mechanism is on Oracle 19, 18, 12, 8, 10, doesn't matter. I think the same mechanism works for a long, long, long time. So let's get back to our AWR. For X3, we had 87 waits of this wait event. For X7, 260. And the total wait was 24 seconds. And the total wait on X3 was 3 seconds. This is a very, very big difference. So in here, we can say that there was something very, very unusual going on with Exadata X7. So what application developers suggested? Well, they said that maybe not all objects are valid, or there was some kind of mistake with the migration and so on. But we knew that it couldn't be true, since, well, we migrated using DataGuard. So this was a physical migration, and the patching level and everything was actually the same. So once you see the SQL text, everything, but literally everything, starts to make sense. Please check this out. Let me show you the SQL text as it was. So the SQL text was like this: update set arg0, arg1, and so arg3, and so on. So what does this update tells me? What the SQL text tells me right away? Well, it tells me that it was not a PL SQL, right? It was something else that was calling a database and updating this row. So the thing that was being executed, the SQL that was being executed by a remote app, occurred to be a Python application that was doing the job. So the same Python script running on X3 causes less problems and shorter transaction queues than it does on X7. Now, exactly why? Let's go to the security, maybe I will be able to let it go and show you what's going on with Wireshark. Okay, bear with me. I also had some kind of operating system update and new permissions had to be set.
Didn't notice.
Shit, a lot of libraries has to be accepted. So apparently macOS thinks that Oracle libraries are dangerous. Maybe it's true. I don't want to go into this right now. Hacking session will be another time. So let me show you what is going on by using Wireshark on the virtual interface. So let's start our sniffing. I'm going to execute update once again. Okay, so this is our update. In here, I will apply a filter. This is our update. From my client with IP end .1, I requested over TNS protocol a request with user OCI functions to the server. And in here, you can see the SQL text that was being sent to the server. And then the server responded with information that, okay, I executed your update. And then I, as a client, responded to the server, acknowledge. So, okay, I understand that you executed an update. So if I perform a commit from a client like this, I see again, please perform a commit. Server says, okay, I performed a commit. And I say, okay, I'm really happy you did what you had to do. So as you can see, for a simple transaction that goes like update and commit, we need to transfer 6 packets over the network. So the code that was being executed by a customer looked something like this. So an update and immediately a commit. Could you please, someone could please mute, Luisa, could you please mute everyone?
Yeah, but if I mute everyone, I'm gonna mute you.
Okay, mute me, I will unmute myself. Okay, muted. Okay. So this was the code I was talking about, right? Someone was executing an update and then committing an update. So what is the length of takes role of contention? Well, it goes actually from here to here to the commit. So the length of the transaction, immediate transaction like this, is from execution of an update, so 1 packet, 2 packets, 3 packets, 4 packets. 4 packets has to be exchanged between client and a server in order to perform update commit. As Radek said at the beginning, and I said also, I also gave you the same information, the distance between between the client and the server was about 10 to 14 kilometers, not a lot, but the amount of hops between, so switches, firewalls, rules, and so on, gave a difference of quite a few milliseconds. So we got from sometimes from 20, 10, 15 up to hundreds of milliseconds of
round trips time.
Round trips. Thank you, Radoslav. So the round trip time was much longer for a single packet from a client to the server. Thus, the more transactions people were trying to do in the same time, the more sessions that they were generating, the longer each transaction was lasting, causing a domino effect, and everything was piling up and piling up and piling up, and that's why we had a serious performance problem at the end. So this is something that you have to consider each and every time. You have to ask yourself a question: does my application use a smart DB approach? Does my application use PL SQL? Because the solution in this case would be to transfer the same logic to the simple PL SQL procedure package function that would be executed from Python, and update and commit would happen at the database level, because and thus it wouldn't require this amount of packets round trip. And this is especially important if you really want to go to the cloud, because your round trip time may be much longer, and you really have to think about those kind of things. So this was the first problem, which started as people as a database problem, and people saying that this is Exadata Clouded Customer problem, and ended up as, well, this is well, in the best case, network problem, but actually this is your application problem. Your application is not written in a way that allows us to put a server farther than a few meters from a database. Okay, Radek, can we go? Can you show us the next problem? Can you take?
You have, yeah, but you have to stop
your
sharing, please.
Stop sharing.
Thanks. All right, so so once again, to summarize it, this is the result which we received from the JMeetup perspective, and what we explained at this place is this situation when we hit longer logons, user logons for that test, and it is connected with row log contentions, and at the end, as Kamil explained, RTT, so round trip times, will have its impact on prolonging those wait events on the Exadata CC or X7 side. We will leave the story of that as I call it, yellow task for the another sessions. What we wanted to show you as the second problem which appeared. I think it will be nice connection with this, which Kamil already told, that the first problem was at least due to the network problems, because there was another situation, another case reported to us that some another kind of activities were poor, let's say. So we've got the same situation like before, but right now the let's say application, but at the end I will explain that this was some kind of report module. It was application, let's say, a piece of software which was producing reports for some kind of web portal. But in this case, in this second problem case, we had server on CC side. So there was not the same situation as before, where the application was placed physically on the same site as X3 Exadata. In this scenario, we have software which is physically placed on the same site as Exadata Cloud.Customer. So the theory and the idea which we explained before, that this distance and those hops, those active network hardware and software pieces were prolonging round-trip delay times, let's say. So in this scenario, application was once again all right with performance when it was connected to the X3, but beside the fact that it was physically on the same site as CC, the performance was once again poor with the Exadata CC. So this is problem which appeared to be really strange, because this is in argue with this idea that those this physical distance between Exadatas in that case have something to do. So analysis, yeah. Analysis. So at the first place, we were able to find out the most important SQL statement, which was let's say, or the important, maybe not the most important, but very important piece of that test. So we identified SQL. We find out that the biggest, from the time perspective, when you are looking at the wait events connected with that SQL statement, we found that the biggest wait event which was connected with that SQL was TCP socket KGAS, which was once more many times longer, many times bigger on Exadata X7 side. Here in example, you can see that for that particular SQL statement, average wait time on X3 was 25 milliseconds, and on X7 it was like 1000, almost 500 milliseconds. So huge difference once more. Let's remember the fact that right now the application physically is on the same site as X7. So that was really strange. And to be precise, we have to explain what TCP socket KGAS is, because as you can see, this is not a type of wait event which is connected with a client-server communication, but this is kind of wait event which appears when database is calling some external resource via UTL HTTP package. So whenever database is calling UTL HTTP external service using that package, you will receive this wait event TCP socket KGAS until that call will end, let's say. So that was the biggest wait event which we have seen. So we started to dig deeper. From the HWR 10-minute period report, you can see that yes, in fact, the TCP socket KGAS is the highest, the biggest wait events which that database faced during that 10 minutes report. But another important thing which we identified when we were digging in that statistics, we find out that during that 10 minutes, which obviously repo was created, logons cumulative statistics shows that there were slightly almost 9 logons per second, which took like almost 5,500 of logons during 10 minutes period. That's crazy number. So when we started to discuss with the guys on the explanation how the reports are working and what is behind that reports, we find out that whenever they call, because there were like several kind of reports. One of those reports was executed within the database. So huge amount of reports were created in that manner that database was calling external service using UTL HTTP package. This external piece of software, which was that application which I showed you on the first slide. Sorry. So that was the application which was called using, so the database which was running here was using UTL HTTP package to call this piece of software to create a report by it, because it appeared that the report itself, not all of them were created like this, but those particular reports were created. That database was calling this piece of software, and that piece of software were creating the report on its own, let's say, instance, and then it was sending it back to the database. So this is some kind of reports, and this is the way how they created the idea. But what's more, we figure out that whenever this UTL HTTP package was called for that web service, let's say, to create the report, this piece of software was once again doing connection to the database, because it has to grab all the data needed to create the reports. So it was creating another sessions, another logons were appeared on the database. It was grabbing the data, it was selecting the data, sending them back to the application. Application was creating the report, and the report was written inside the database, and once again it was doing it was creating the session. So every time the application, this piece of software was or had to go with the interaction with the database, it created session. So whenever those actions were happening, and number of that actions was big on the database, the UTL HTTP calls was quite huge. It was much bigger, it cost much higher number of logons from that application to the database, because it has to grab the data and and still create the report. So yeah, so we find out that the number of logons, number of cumulative logons which we've seen for that database was huge, and the fact of it itself is insane because it shouldn't be done like this, but okay, that was the idea. But from the other hand, on the other hand, the whole theory about the RTT and the physical distance of application, let's say, was not working in that case. I believe, Kamil, I don't know if you have prepared it, Kamil, right now, because we have this nice visualization tool which can show you logons in very nice manner. Can you show that, Kamil? No, I cannot hear you. Okay, Kamil is
Unmute. Okay. I'm
oh
unmute.
yeah, right now. Yeah, cool.
So yeah, I have the visualization. Could you please stop sharing your
you have, okay, cool. Let me stop. Okay.
Awesome. So let me show you. What is it all about. Okay, so how you can see the overall picture of your system, because well, the things that we are showing you are well the final result, the results of our investigation, but we had to go to this point somehow. And one of the best ways to see what's going on is to see a big picture first and then drill down and try to understand what is going on, right? So we created a few tools that will help you do this. They are all available on our GitHub on GitHub/Orasic. Okay. Here on GitHub/Aura600PL. So those visualization tools are in AWR scripts.
Mm-hmm.
If you have diagnostic pack, stats pack scripts. If you don't have diagnostic pack, Stado for network analysis, but I don't think we are going to cover Stado today. This is for then another meetup, because yes, there will be another meetup. Luisa, please be happy.
I am crazy happy.
And in Trails file passes, you will find listener analyzer. So first of all, if you have a set of AWR reports or stats pack reports generated for some period of time, like here I have a set of reports from 1 week. 1 week? No, it's not 1 week. 1 day of work. It was a Monday, so all snaps and all reports were generated. They are in here. So I have a set of AWR reports, and I can use a Python script, AWR analyzer, in order to get this result that will show me the visualization of network problems. And those are the network problems from the wait event that Radek was telling you about. So TCP, KGAS, TCP socket KGAS, right?
Exactly.
This is a member of network, and in here you can see a classical Monday on 10 CPUs on virtual machine in X7 environment, and this is a network peak in Exadata X3 on 16 CPUs. So the peak was 1,000 seconds for this weight class, but usually it was like 400 seconds, 600 seconds. And in here on Exadata X7, you can see that it is usually higher than 2,000 or 1,500, right? So it's a big difference. You can see also load profile per second, so DB time, DB CPU, top sequels by elapsed time, division for time model, and in here, what could be important for us is the amount of time that Oracle is working on connection management. If we double click on connection management called elapsed time, we will see that, for example, here, Oracle spent 60 seconds per, wait a second, let me check if this is 30-minute interval. Yes, this is a 30-minute interval. So 1 minute for each 30 minutes was the time spent for managing the connections. And for example, you could see in here how many, how many rollbacks. This is also important, but we are actually we want to see how many logons was there. So in here we had 4.4 logons per second. And if you go to the listener logs and visualize them, you could see that, for example, in here from this IP address, which was a server report, we had more than 17,000 connections to the database each hour. So based on those tools, you can see like a big picture and you can see what's going on. Like, for example, if you have what kind of latency you have on the disk in user IO wait class, how many blocks were read, and so on, and so on. So we use those tools that we wrote ourselves, to be able to look from the top and then try to guess where to drill down and look for the problem. And those were really comfortable tools to compare the same periods of time, execution of the same application in different database environments. Yeah, okay.
Yep.
So back to you, Radek.
Right. Right. So as you can see, it produced like insane amount of connection to the database. But the strange thing was that the same amount of session was created to the X3, and what we what the customer told us that, all right, but whenever you run those reports on X3, it's okay. Whenever you run those reports on XRCC, it's slower. It's much more slower. Users are complaining. They have to wait longer for their reports. So basically, yes, the amount of logons is huge. It's insane, but still the same number here produce better report results. So what is the problem exactly? We excluded the RTT problems with the distance because now physically the application is on the CC side, so it's not the network delay problems, probably. So what we did, okay, so let me back here. So basically during those analysis time, we were trying different approaches, different tools, different things we were doing during that time. And there was some time when we figure out that basically there are periods whenever you are trying to log on to the database, you have like huge delay, about 4 seconds, and it happens like from time to time, and basically it appears on ExaCC and it doesn't exist on ExaX3. So basically using, for example, SQL Plus to log into the database created 4-second delay whenever you wanted to log in. So we did strace for the process, which showed us a little more information what was happening. Basically, we were doing strace on TNS ping to the database using fork switch. So we were also tracing the child processes which were running whenever TNS ping was running. And when we are examining the output trace file from that tracing, we find out that there is some kind of poll call which lasts exactly 4 seconds, and this poll is executed on socket number 5, and socket number 5 is connected with NSCD. So basically, NSCD is name service cache daemon. This is daemon which is running on the Linux operating system, which is responsible for caching, for example, DNS responses, DNS service responses. But not only that, it is also responsible for caching like passwords, groups, and other stuff. But it is also responsible for caching DNS responses. So basically, we started to figure out that there is something wrong with how DNS is used by the operating system itself. Then we connected the fact of this longer DNS execution with the fact that this piece of software, which was running reports on both Exadata, was using, in that case, JDBC thin driver to connect. And JDBC thin driver architecture differs from OC because during, let's say, operating and creating the session with the server, the fact is that it is perform DNS lookups and reverse lookups. So it is using DNS. And this is the, let's say, the point where all the puzzles started to create some kind of picture to us. So then we started to use Wireshark to generally diagnose what's happening on the DNS side. Yeah, so sorry, I had to anonymize a little bit those information, let's say, here. So using those blue rectangles. Basically, what we see here is Wireshark dump and analysis from running those TNS ping. So basically, normally when from the operating system perspective, you are trying to resolve some kind of name to the IP address, it will use DNS service. So because we want to do that faster, or there was some kind of, let's say, problems with DNS, with the how long it takes, you can speed up this piece of activity by running name server caching daemons. So you are running cache for the DNS on your local system. So basically, this is what happened here. But cache itself was what we think now is not the problem at the core of the structure, because at the core of that issue, because normally whenever you run DNS resolution on the Wireshark, you can see that the first packet which ran request for the DNS service is asking for particular name, and let's say that the source address is 82 and the destination is some name server. So the operating system is calling in parallel So packet by packet, it's the same, the source is the same, so 82 and 82, but the first packet with the request goes in type A, which is IP4, and another packet, 79, which comes also from the same source, asks for the name for the type AAA. So this is the IP6, and this is very important. As you can see here, the response for the first IP4 version request is sent back in packet 81. So here. For IP6 version, request is returned in packet 180. So right now, when we will look in answer for the IP6 request, so request in 78 here, the first request in IP4, we've got our answer, of course, and the duration of the answer. It's like sub-second, yeah? But when we look at the answer for the 79 request, which was IP6 request, we will see that the duration for the answer was like 4 seconds. And this is the same as we see on the S-trace, yes? This is the time, this is the packet, the response packet, which took 4 seconds. So the same amount of time we've seen on the S-trace level. So basically, yep.
We have like 5-10 minutes more.
Yeah, okay. I will finish in like 5 minutes.
Okay.
Thanks.
Do you have a meeting today, Luisa? Are you?
I'm very busy. I'm very busy. I have other plans. So can you just?
You're going out, yeah?
Yeah, I'm just already in my outfit. So.
Cool. Okay, just let me finish, and we are approaching to the end of that story. So there is explanation for this, for such behavior on the how DNS is implemented in basically in library which is used by kernel in Linux. Basically, we are talking here about glibc, so library which is responsible for resolver for DNS in the Linux. From version as far as I remember 2.9, it implemented some improvements in speeding up how the system will resolve requests, and this implementation was exactly what we have seen, that basically resolver is asking in parallel DNS services for IP4, and just packet by packet it goes with the IP6 version, and it shows that there are some kind of network devices, active network devices, which have problem with that. They cannot send back those answers properly. As far as I were able to understand that problem on those network levels, the cause of it is some kind of active network devices in between on the trace, on the way from the Linux to the DNS server. So they were breaking the communication, and that's why the answer for the, let's say, process which were asking for the DNS resolution had to wait for both answers, for IP4 answer and IP6. It couldn't return to the process answer just version by version of IP. It has to wait for both answers, and then it was returning to the process. So basically, you can switch off that feature in resolve conf on the Linux level. You have to add option single request, which will turn off that parallel request for both IP4 and IP6 requests for DNS. And whenever you put that option inside your resolve conf, the Wireshark dump will look like this. So at the first place, you will ask the DNS server. So we have the same source, 82. We have a DNS server. So the question is, give me IP for the name, blah, 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 type A. So this is IP46 packet, sorry, IP4 type of packet. On the next number of packets, so 45, 47, we've got answer for that. So immediately the server returns the answer with the IP4 version of, let's say, request. So we have answer, we waited like sub-seconds. And then after receiving the answer for IP4, resolver is asking once more DNS server, but this time it's asking with IP for IP6 version for the request, and then it returns its answer. Okay, some kind of answer with this time in sub-seconds. So this serialization of request will much improve your request, and taking in mind that we've got so huge, so insane amount of logons per second using JDBC, which was based on basically doing some kind of DNS or reverse DNS lookups. And whenever those delays were happening, they were produced in those sessions. So basically, whenever database wanted to create report, it was using UTL HTTP package to connect to those web service. This service was doing lot of sessions to the database, back sessions, and was doing some kind of stuff. And during creating those sessions, those DNS problems were appearing, and delays were like multiplicating each other. So that's why TCP socket KGAS was so big on X7 CC. So basically the solution for that problem was just simply putting this option into the resolve curve. So once more we have like information, okay, database is slow, something is wrong with the database. The solution was DNS, and how Linux and it like default system resolver is doing name resolution basically. And that's the story. That's the story of problem 2, which I think was a nice addition to the first problem when the application physically was placed on the same side as X3. We've seen also some kind of problems here, the same kind of problems, different approach, different service, different drivers, different solution. Anything you want to add, Kamil?
Well, since we have to add just a finishing touch, maybe. Well, you've seen 2 problems that were both focused on the network area, right? And one of the problem was solved by the full stack trace and getting from the slow application performance, AWR reports, time model statistics, up to strace on operating system level, and fixing a DNS calls. The other problem was a pure application design problem combined with the network performance problems. So the problem with the DNS was a bit harder to diagnose, and we spent actually quite a lot of time reading S-trace and playing with S-trace switches in order to understand on which syscall level we have a problem. But in both cases, my question, why Kamil drinks wine? This is a beer. It's just one of the POUG glasses that you all gonna get. But I also have wine because my beer has ended. No problems, Monica. So in both cases, please mind that actually the solution was, the approach to the investigation was the same. Look from the big picture perspective. Look at the behavior of the application and the database using visualization tools, and drill down. But you can drill down only if you fully understand what's going on each stack level, right? So right now, well, we say that cloud changes everything. Yes, it does. With cloud, you as a DBA, you as a developer, you have to know much, much more right now. You have to understand network, disk, operating systems, everything, if you want your application to work properly. And one last thing, one of the toughest problems you can actually hit is when you can't see, when your time goes away in AWR reports and in the general visualization. So you can't actually tell why the app is running slowly right now. And actually, there are some ways of understanding and feeling, guessing where the problem is and tracing it. Well, we are going to show you some cases based on our experience with this and other cloud-like implementations on the next meetup. So on the next meetup, please expect another full stack trace approach from the network perspective and network latency with our other tool called Stado, SQL Trace Analyzer designed for Oracle, which will show us the difference between user calls, executions, and we will drill down from slow SQL from app perspective through a slow SQL seen from database perspective, and instance statistics like user calls, executions, and well, Wireshark explanation again of it, and the whole summary, summarization and correlation between the results from our Stado and the AWR. So this is coming next. Luisa, I'm sure you are happy because you know that we are already prepared. And thank you for listening to us today.
Thanks.
Yeah.
Yeah, Luisa, you're doing it rockstar way.
Now you're doing in non-style way. We can't hear you, Luisa. You are muted.
And now?
Yeah.
Much better.
Ah, you are in
I
backup.
am on the 2 devices because I'm like
Parallel sessions.
yeah. I'm gonna stop like this. So okay, so there is a question, Kamil. I don't know if you answered it already, but because I have no idea what are you talking about. But there's a question from Elisa. It's so from your point of view, is CC credit card version fine? There's a joke? This is not supposed to be a joke, but if it was, it's okay. Never mind. So this is why I cannot be a moderator. Like,
Well,
no, it's a tough question. To
it's
be
a
honest.
tough question. It is a credit card version is a good summary, but
please stop.
maybe the best way would be, Radek, for us to create another session only about Exadata Cloud Customer and features and bugs and features that comes with it.
Back to the past, basically. Yeah.
So
it depends. It depends. The answer is not simple.
Okay, I could tell. I could say I could answer. If the answer is it depends, I could answer that. But okay, so we're gonna have another meetup, and we're gonna try the webinar version because it's probably more professional. But if you want to speak during our meetup, please contact us because yeah, thanks. Because we want you to be a part of it as well. And I know that I cannot count on Kamil and Radek forever. And I know they are not prepared every time. So if you want to join us as a speaker, please contact me during mail or Facebook or Twitter, whatever, and we will give you the stage, the virtual stage. That's cool. That's cool. It was as professional as we are. So semi-professional with a lot of beer and a little bit of charm.
And shitload of improvisation.
A lot of improvisation. A lot of improvisation. And I just want to add that each Wednesday and Friday we had this little Zoom meetings, and it's like POUG and friends or OUG and friends. And if you want to join this kind of meetup, there are some pretty cool people there. We are basically just drinking and chatting.
And that's all.
And that's all. So
just looking at each other and drinking.
And looking at each other, and we're having fun. And if you enjoy us, yeah, please contact us. I know some of you are, like Łukasz and Tomek were with us, so please feel invited. And if that's all, I think we're done. I will see how it went, like how the video was, and if it's good enough to send it to people, because as I told you, it's our first time, so I'm not sure if it went well. But if not, I think I will force Guy to make something shorter and record it, right?
Yeah, we can do it. Actually, it's really strange to do the session like this, not seeing you people and interacting with you, because the most fun we have is during the interaction. And I see a lot of speakers in here who can confirm it, right, guys and girls?
Sitting in the hotel corridor.
Yeah. I just have an idea from the top of my head. I see a few people here on this meetup who can also say a few things about Exadata Cloud Customer, because
Name them.
That those people are working with this product right now, and maybe we could go and figuratively and talk about it, maybe prepare some extensive session about the product itself and good sides and what to be aware of. Right, Flora?
Sorry.
Until the last moment, I thought you would not say my name, but
I'm looking at you and at you, Martin, wherever you are. I saw you somewhere, I think. Okay, so we'll get back to this. So, any questions? You can all speak right now.
Yeah, you can literally speak. You
Beer
don't.
is almost over.
I heard something.
We have to switch to wine now. The beer is over.
Ah! Okay, so if you don't have more questions, I think we will finish here. And thank you so much. I hope you liked it, and please forgive us for all smaller and bigger mistakes. We will get better with time. And let's stay in touch as we can in this strange time. And I will mail you. I will try to sum up this. See you next time.
Okay, great. So Luisa will write an article based on our topic.
I'm already on it. I'm just waiting for Kamil's input, and it will be ready soon.
A book.
Okay,
Do a book directly.
some things you can find already on our blog, on blog.ora600pl. So you can find some summarization. I'm sure there will be more about DNS coming soon from Radek. Okay, he just...
Radek is pretty surprised with this idea, but
I'm already on it. I'm already on it.
Radek was surprised that he's going to speak today, so...
yeah, Radek will prepare after me the materials.
Book, yeah.
Okay, guys, thank you so much. I will try to send you the links that Kamil will tell me which one, right?
Okay. Yeah, if I
Thank
want.
you. Bye
Bye.
bye.
Take care, guys.
thank you so much. Bye.
See ya.
Bye, thank you.
Bye.
Does that mean that we need to turn off?
You don't need to turn off.
You don't need.
No, you don't need to. We can be in your apartment.
Your beer with us.
We can stay here.
It's your home. You can do whatever you want.
Thank you.
Yeah.
With this, I'll go home to my family.
You have to what, Neil?
It's
Yeah.
either this or go to my family.
No, let's stay here. Stay here.
You have to.
I have a beer.
That's good.
I have to take something as well because I'm out.